All right, this is section 7.2, public key cryptography, and we're talking about the RSA crypto system. And it was invented in 1978, and the basic idea is that large numbers are hard to factor. So here we have the basic idea is that, say you have two primes. I'm going to work with really small primes at first. So P equals 5 and Q equals 7. Then I'm going to let N equal 5 times 7, which is, of course, 35. Now, the way RSA works is that there's really like two, when we think about Zn, there's really two moduli going on with Zn. So if I find a, that's because when you're adding, you're working kind of Zn. And then when you're multiplying, you're kind of in this Zn star, right? And so then the amount of things in Zn star is, that's the Euler-Totient function of n, which is equal to, if you have a number that's a prime times a prime, is equal to p minus 1 times q minus 1, which is equal to 4 times 6, which equals 24. So, what this means is that if you take any number, so any x in Zn, then x to the 24th power is going to be equivalent to 1. Mod n. Or it could be equivalent to 0 if you have like a factor of 5 or a factor of 7 in there. So if x is in here, if it has no factors of 5 or 7, then to the power of 24 is going to give you the identity. And when the primes are really, 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 really big, your chance of being in Zn, picking an arbitrary number, is pretty good. So that means that, say my message is going to be say my message is going to be 6. Then what I can do is I can pick an exponent that is forget the properties I need for this. Let me just for now just say you pick like an exponent equals something. And then for RSA, you basically say x goes to x to the e is encryption. and then call that y. And then when you send y back to there by taking y to the power of d for some d, that's decryption. The main idea of RSA is that, so basically RSA is taking numbers to powers inside of a mod n. And the main idea is that you have a public key. Everybody has a public n and e. And everybody has a private key d. And the only way to figure out what d is for somebody else is to factor n. So to find d, we need to, you must factor n. To compute, you need to complete the Euler-Toshin function of n. And the only way to compute the Euler-Toshin function of n is to factor n. Thus, what this Christoph system does is it relies on the fact that it takes a long time to factor big numbers, that your private key stays private as long as nobody can factor your n from your public key. Okay, let me go back to the textbook. So let's look at this example of a little bit larger example of P is 23 and Q is 29. And E is 487. You know what? We need to do this in Sage, don't we? Because there's really, all of this stuff is really hard to do by hand. So this never really happened until computers were invented. So let's put my Sage over here and my textbook over here. Okay. So let's create this. So P equals 23, Q equals 29, N equals P times Q. And then the Euler-Totient, I can just compute it as P minus M times Q minus M. P minus 1 times Q minus 1. So then print P, Q, N, M. So P is 23, Q is 29, N is 667, and then the Euler-Totient is 616. And then we let E equals 487. And the way to check that E will work is if it's relatively prime to M. E and M. So as long as the E, your exponent, and not the N, but the M. So there's like N is, when you think of like, I'll keep using N and M for the two moduli going on. N is like the base moduli, and M is like the exponent moduli. Okay? So it's important to remember that there's two moduli going on. And so then say if our message is x equals 25, then what you do is, and there's a couple ways to do this in Sage, but we're going to want to do everything mod n. So let's just let like define this ring of the integers. Now, again, this is like using the power of Sage here, and this will help us in some ways and hurt us in other ways, because if we work inside of a Sage integers mod n, then it will always do the modulus for us, and that's great. And it will always do the modulus for us, and so sometimes we can mess up. So we oftentimes think of integers mod n, sometimes as like mod n, and then suddenly we want to think of them as integers again. So we just need to be careful. So x equals r of 25. So I'm just going to take r of 25, and then the y equals x to the power of e. So print x and y. So x is 25, and then my encrypted number is 169. Okay. Then to find d, you can just do to find d, you can just do x GCD of e and m. And so 191 times e minus 151 times m is 1. That means that d equals 191. So then if I compute z equals y to the d, x, y, z. So then x is 25. I took it to the power of 169. No, took it to the power of e, I got 169. Take that to the power of d, and I get back to 25. Okay. So notice that to find d, I have to work mod m, because e and d are both exponents. So they're working, in a way, they're kind of in the upper moduli. There's like the lower moduli and upper moduli. And so for finding e and d, that's what's going on. So let me pull up notebook, put it over here. So just kind of explain what's going on here is that x to the e, you compute x to the e mod n. So when you're doing computations, so basically like when you're computations for the crypto system are working mod n. Okay. But then you say, when you say like you want to find d, so you want to sort of find d such that it undoes e. You want to find d such that e, x to the e to the d equals x mod n. Well, to find d, you have to work in the level of exponents. And the exponents are, you remember that like z n, the size of it is equal to m. So m is like the size of all of the numbers in Zn that are units, the unit group. And so we know that if you take something, so you're just finding kind of the inverse. So d, if d equals the e inverse, mod m. Because it's at the level of exponents. Does that make sense? Okay. Thank you, Katie. I need I need a real live audience. All right. So that's what we did there. And so in order to compute D, we needed to know M. In order to know M, we needed to factor N. If I know how to factor N, I can compute M immediately. If I don't know how to factor N, then I have to like factor. Okay? And so let me just demonstrate how factoring is hard. So factor 10 to the 20. Let's even do like a +1. So that's not too hard. 10 to the 20th power, not too hard. That's the wrong thing. I need to do that. So basically, it's like 0 amount of time to factor that. But 10 to the 40. Okay, I need to like maybe pick something else. So Sage is smart and he uses all the tricks there are for factoring. So if I create P equals random prime, can't remember if random prime is 10 to the 20. Yeah, that works. Okay. And Q equals random prime 10 to the, let's make it I. And I equals 20. And then factor P times Q. Okay, so I was able to do that pretty easily. So P and Q are from 10 to the 30th, and there goes my computer. So that's weird how it's not, it took a while, and yet it's not saying it took that long. Let's say we have to the 35th power. There it goes. It's thinking, it's thinking. So it's not too hard to come up with, like it's really easy to come up with giant numbers, but it's really hard to factor something that is the product of two giant numbers. And so it's really easy for your own computer to just like come up with two big primes, multiply them together. That would take like all the computers in all the world years to factor. So that's what creates the safety of this whole system, is that factoring really, really, really big numbers takes a lot of time, because it's basically like the naive way is just like, are you factorable by 2? Are you factorable by 3? Are you factorable by 5? So on and so forth. Okay. I'll just leave that going. So back to the book. Okay. So this is going back to theorem 618. So back in chapter 6, we had Euler's theorem basically, which said that like if you're equivalent to some like by being, if E is 1 modulo the exponent, then you get back to yourself. Okay. So then there's also, you can do message verification. So you can sign something so let's do it this way. So let's start over again over here. Well, let me actually just restart the kernel because I don't have time to go through and see that. Okay. And then let me change that number back to a reasonable number. Maybe I'm supposed to do time it. Anyway, so now, let's say I have 2 people. So, anyway. Anyway, I forget how to do that exactly and show how much time the CPU is using. All right, so all right, example of RSA signing and encrypting. So first we'll do Alice. So Alice has, we'll pick 2 things for her. So P A equals random prime. We'll make it around 2 to the 10 to the 10th. So we're not going to make one that's super secure, just as an example. And Q A equals random prime 10 to the 10. And then I want to print them. PA, QA. All right. Now, what I'm going to do now is if I want to make it so that I can use these over and over and over again. So I want to make random primes because we humans are not very good at picking random numbers. And yet, if I just do it like that, then there'll be different primes every time. And that could be bad for as far as my setting up a crypto system because Alice wants one thing. So we'll make now like kind of set them to be those things. Okay. Then NA equals PA times QA. And MA equals PA minus 1 times QA minus 1. And then you can just like guess out of E. So I'm going to guess like 151. And then check it. And I guess I should call it EA. Guess and check. So I guess 151. I check if it works. It works. As long as it's a prime-ish, then your chances are good. If you look at up here, we should probably print out NA, MA. So M is always going to be even, so your E can't be even in order for it to be relatively prime. And it's often going to be divisible by other small primes. So like picking a prime that's kind of somewhere in the hundreds is generally pretty good. So then EA works. So then for Alice, we need to compute Alice's decryption. And that is going to be it's the best way to do this. XGCD of EA and MA, and I only want the second element in the XGCD. So what's DA? And I want it mod M. No, MA. You don't know, Sage doesn't know what I'm talking about. There we go. Okay. So this is one way to do it. Another way to do it was just, so DA, it needs to be the inverse of EA, and this is one way to do it. Another way to do it would just be like define the integers mod MA and compute it that way. So lots of ways to do it. So then check what is EA times DA mod EA times DA mod MA. It works. Okay. So now, let's do it for Bob. So similarly, we need these things, but for B. So in a way, this could be like my random generator for both of them. So then I just need this, but for the new different primes. And then this is for Bob, not Alice. So then compute stuff for Bob. MB, B, QB, NB, MB. Okay. Then I need to guess a encryption number for Bob. I don't know, 171. And then check it. GCD of EB and MB. No, that does not work. So let's try another thing. 173. There we go. Then I need to compute DB. Well, I can just copy and paste here. Need to compute DB. So it's going to be the inverse. Okay. And then do the double check. EB times DB mod MB. Yep. So DB undoes EB. And so now let's so we computed stuff for Alice and Bob. Then let's make we're gonna make a message from Alice to Bob. Message from Alice to Bob. Now, there's a method here. So it depends on whose n is bigger or smaller. So if Alice's n is larger than Bob's, then she needs to decrypt first and then unsign. Well, first we gotta encrypt, but so let's look at NA greater than NB. So Alice's is bigger. So you always do the smaller n first. So let me just write that down here. When we encrypt and sign, we do the smallest n first. So let's come up with a message. 1, 2, 3, 4, 5. Okay, there's my message. Then I'm going to, so Alice knows her whole key. She knows her N and she knows her E and she knows her D. Okay. Bob, but she doesn't know, she knows Bob's N and she knows Bob's E. She does not know Bob's D. Okay. So she uses what she knows. So we're gonna make, I don't know if I want to do this with the Sage or with, if I want to do it Sage-ish or Python-ish. I think I'll do this with Sage because we're going to take some big powers here. So RA equals integers mod NA, and RB equals integers NB. Okay. So Alice is going to take her message and she's going to use Bob's. She's going to do Bob's thing first. So she only knows Bob's N and E, so she's going to use those. So she's going to take, she's going to encrypt it first, then sign it. Is equal to R of message, R using Bob's thing first, of message to the power of EB. We can look at encrypted. All right, so there's the message that's encrypted. And then right here, Bob's N is smaller than Alice's. So Alice will first encrypt, then sign the message. Okay, so there's the message. Define the Sage things. Encrypted equals that. Okay, so then signed equals, and then actually, let's put it, when we're done, let's put the encrypted back into the integers. So let's do it in two, I'll do it in 2 lines just so that we kind of, you can see what's going on. So now it's, I put it into the Sage integers mod NB because it makes this, Sage knows how to do exponents in modulo n really quickly. So then you're not going to slow yourself down when your numbers get gigantic. Whereas Python can do dumb things if you're doing it with just base Python. So there's smart ways to do it with Python too, but Sage will do the efficient way for you automatically. Whereas Python is just like you can do whatever and you're free to do it the dumb way. So because when your numbers get gigantic, then you're taking like multiple like big powers of things. So that can slow your down. So then signed, we go into Alice's n, we take encrypted, and then we take the power of Alice's secret key. And then we'll bring it back into the integers. So there is the message. So Alice sends this message to Bob. Now, Bob will unsign and then decrypt the message. So, so Bob takes the signed message and he unsigns it. R of A of RA of signed to the power of EA. So Alice's public key. So Bob doesn't know Alice's private key, but he does know her public key. So he can do that. And then he'll make it back in the integers. And notice that number is the same as that number. So he's gone backwards one step. So then next, Bob will decrypt. So then decrypt equals RB of unsigned to the power of Bob's secret key that nobody except Bob knows. Then we'll put it into the integers. And I have the message, 1, 2, 3, 4, 5. Okay. And I'll make this sheet available to you guys. Now let's say Bob wants to then reply. So let's say now Bob wants to reply and send a message back to Alice. Okay, so let's pick Bob's message. It's going to be, he says, well, 1, 2, 3, 4, 5. Well, I'll tell you 6, 7, 8, 9, 0. It's really interesting messages they're sending back and forth. So this would be like in a different sheet, basically, because it's, but so you would define these guys, although I'm in the same sheet, so they're already defined, but I'm just going to kind of, for the sake of doing this, then because Alice's n is bigger than Bob's, since Alice's n is larger than Bob's, Bob will use his n first. So Bob will sign his message first and then encrypt. This is something that's not covered in the textbook, but as I've done these message board problems with classes, we have figured it out the hard way that this had to happen. Okay, so Bob's going to sign the message. So signed equals R of B of message, the power of, so Bob, when he's always using his private key when he's like making something secret. So his private key. Signed equals ZZ. Signed. And show me what signed is. So there's the message. So Bob signed it so that Alice will know that it came from him, and then he'll encrypt it. So then he'll encrypt it. He'll encrypt it using Alice's public key. He doesn't know her private key. And then we'll put it back into the integers. So then that's the message. This is the message that Bob sends to Alice. So Alice, knowing her n is larger than Bob's, will now decrypt and then unsign the message. Okay. So then decrypted equals R of B. No, decrypted is she's decrypting, so she's using her method of encrypted to the power of her secret. So E for encrypt, D for decrypt. All right, DA. Decrypted equals R of CZ decrypted. So decrypted is that number. Now notice it's the one that's a couple ones above. And then she'll unsign it. So then unsigned equals, so Bob signed it using his secret key, so she can use his public key to unsign it. So decrypted, power of Bob's key, and unsigned equals CZ. Unsigned, sign equals 67890. Okay. Now let's say Charles wants to intercept the second message. So Charles is the bad guy. So he needs to find the one number he doesn't know is BA. So how is he going to find it? He takes Euler phi of NA the step if numbers are large, the cell above might run for a long time. Okay, so the numbers are small, so Charlie hacks it right away. Then Charlie and then he's got MA, so then he does DA equals X, like basically the computation up here, basically, where once he has MA, he can compute DA. And then once Charlie has DA, he can do everything that. So now that Charles has DA, he can do everything that Alice just did. Also, he can send messages to Bob pretending to be Alice by signing his messages with her DA. Make sense?
Yes.
All right. That's a lot. I'm going to leave this on a canvas, and but for this homework, there is no proof or anything. So let me explain the homework for this section. So for this homework, it's basically Susan compute several RSA computations. So it's completely a Sage, basically. And the homework 7 through 10. So the homework here is fairly simple. It's do these computations. But then the fun part is with the Sage homework from this section. So with Sage 7, which you might want to do first before you do the homework, because it'll help you do everything faster. So for Sage, the exercises are, here's some interesting exercises. That's all fun and games. And then there's a classroom exercise. So for the classroom exercise, what I've done is I've shared an RSA message board with you. And I have my own public key and private key. My public key is, I believe I set it up so it's hackable, but only if you spend like an entire day trying to hack me. But you're not supposed to hack me, you're supposed to hack other people. So what it is you set up your own public key, your N and your E, and then I'm going to send messages to each of you here, and then you guys will respond. So I'm going to ask, it's going to be in the form of a question. And what's going to happen is that the grading for the Sage, where am I at? So for the grading for Sage, so the first 4 questions is like you can do the questions, and then you get points if you can successfully encode or decode RSA messages without another student deciphering the message. And then if you successfully decipher another student's message, you get a bonus one. Okay? So the way this works is you pick a public key that's big enough and safe enough, then you get boom and boom. If someone else in the class picks a weak public key, you can also decipher them for a bonus one. So the number of Sage things to get an A is if you get 2 of these and everything else, you get an A. So if you hack somebody, there's one sage one you don't have to do and still get an A. Okay. And that's what we're doing. Okay. All right, I'm gonna turn off the recording now, and I'm gonna post my Sage worksheet on Canvas.